Hi, in this video, we want to take a look at multiple linear regression. All right, so we finally got to multiple linear regression. Oh, I'm so glad. I've been chomping at the bits. This is when the things start getting like really interesting. This one's getting exciting. This really is like the point of the entire class is right here, right now. The material in this chapter is the stuff that you need to walk away. When you walk away from the course, you need to remember this stuff. I know that there's a lot of material in courses, in stat classes, math classes, physics, that after we're done, we kind of brain dump it. Do not brain dump this chapter. This chapter you need to keep in your head. Chapter 7, this is your multiple linear regression chapter. This is the stuff you always need to keep in the back of your mind whenever you're doing your regression models in the future. Okay, so we've got a model going on. So remember, y is our target variable. It's our dependent variable. And it's what we want to make a prediction on. We want to predict those values. Our goal is to make a crystal ball that tells us about the target variable, y. Now, we could also be doing inference. We could also, like we want to know how much to increase things by. We could also try to be doing to control something like a machining process, like a factory. But for a large extent, a lot of the vocabulary will focus on prediction. And that's just because it's a natural way to be looking at this. But there are other uses of regression. Now remember, all of our x's are our predictor variables. They are independent variables. And when I say independent, I mean that x is independent of y, but y is not independent of x. And the x's may or may not be independent of each other. But the framework is something like, if we've got temperature and the rate at which ice melts. The rate at which ice melts does not influence the temperature to a large extent. I know there's a little bit of fudge in that, but the temperature determines the rate of melting. Melting does not indicate the temperature. That's how we're looking at it, how we're approaching it. All right, now for us, y is always a continuous variable. So, all right, so it's a real number. We're keeping it real, yo. So we're not doing something like Poisson regression. We're not doing logistic regression or anything like that. We're not that far along yet. X are fixed constants, and they are perfectly measured, and they can be continuous or discrete. So something that is very important about this is, first of all, they're constants. And everything we do, we're treating it like once I observe X, that's it. It's done. It's known. There is no variability in it. And we're also saying that those values are perfectly measured. There are other types of models that deal with randomness in your predictor variables, but we're not that far along yet. Okay, so now what is our model? Our model is going to be a degree 1 polynomial. So here I've got intercept, I've got our first predictor variable, second predictor variable, and so on down the line. And each predictor variable gets multiplied by its own coefficient. And then we get an error term or an epsilon term, random term, however you want to look at it. All right, so something that we need to say about this is that y is linear with respect to the coefficients, but it may or may not be linear with respect to the x's. Okay, so got a little bit of light coming in. I'm just going to leave it. So, example of this is if I have just one variable, and if I look at this equation down here, I've got a quadratic on my x sub 1. All right, this is a degree 2. But I can take my data and I can have a column of constant ones. I can have a column of x sub 1s, and I can have a column of x sub 1 squared. And since I can put that onto a matrix, that's okay. It has to be linear with respect to the betas, not with respect to the x's. We can multiply the x's. We can put them through a nonlinear function. We can do anything we want with them, as long as when we're all done, we can represent this with matrix operations. As long as I can do matrix operations to get my model fit, then everything's good. Okay, so what's our equation going to be for this when we're using our actual observed data? So up here, when I have this, notice that I'm not specifying any observed values. This is the theoretical model that I believe to be correct. When I've got my observations, now these are actually fixed constants in real life because I've observed what's going on. What I want to do, I want to find the betas that give me the best fit possible for the data that I have. So I believe that there is an equation like this. In reality, theoretically, there is an equation as a degree 1 polynomial on all of my predictor variables, and then there is the random term, and that tells me, and that if I knew everything about this, I would know everything about y. Okay, that's my theoretical framework as I approach this. Now, down here, what's going on is that when I pass my observed values into that equation, I'll get y sub I after I tack on some random term onto there to account for things. Okay, so what are our assumptions? So we've got 3 major assumptions, and these 3 assumptions, we cannot slack on them. We have to have these have to be correct. If any of these are not correct, we cannot trust the model at all, any way, shape, or form. Now, we can actually make things a little bit looser on it if we want to take a geometric point of view on things, but really, we want to keep it as is. Okay, so just for all practical purposes, this is the bare minimum. All right, so the expected value of the error term is 0 for all the i's. All right, so if I restate that in terms of the y's, is the expected value of y given x is exactly everything that I have except for that error term on there. Now, and something that's important, the expected value of a random term given the x is equal to 0 for all I. You'll notice that the x has no influence on what's going on. Knowledge of x does not tell me anything about the random term. This is something that the notation does not emphasize enough. Also, the variance of our random term given our predictor variables is constant. So something that's important to pick out from this is that there's no x's over here. Your x is gone. Your x is out. All right, so there's no x over here. It's constant. The x has no influence on the randomness. All right, so over here, I can say the same thing, that the variance of the observed y's given x is a constant value. Now, the covariance between the random terms of different observations is equal to 0, okay? And then the covariance between the observed y's is also equal to 0. So this assumption is equivalent to this one. These two are equivalent to each other. These two are equivalent to each other. These two are equivalent to each other. And what we can do, depending on how we want to approach it, depending on which one's easier for the proof, we pick whichever one is easier for us at the given time. So if I'm in a situation where I'm working with the epsilons, I'm taking the assumptions from the left. If I'm working on a proof and I'm working with the y's, I'm going to articulate the assumptions in terms of the right-hand side. Okay, so our 3 assumptions is that, first and foremost, the model is correct in terms of an expected value. Next one is that we have constant variance. And now when I say constants, that's with respect to the x's, the predictor variables. And the last one is that we have uncorrelated observations. If we do not have these, nothing that we talk about works out. And we need all 3 of these to be reliable. Otherwise, it's a garbage in, garbage out situation with our data. And we don't want to be building models like that. All right, so the next thing that we'd like to tack on is that we want to say that that random term is normally distributed with mean 0 and variance sigma squared. Okay, remember, if I have covariance equal to 0 and normality, that also gives me independence. That's very good. Now, why do we like that? Why do we want this normality assumption to be tacked on there? Well, if I know the distribution, then I can do hypothesis testing. To do hypothesis testing, I need a p-value, right? To get a p-value, I have to have a distribution. If I don't have a distribution, I don't have a p-value. And so for me to be able to do hypothesis testing, I need to have some kind of distribution to work with. And so for most of the cases with linear regression, we're going to assume normality of the error term. Okay, so if I go through and I apply my equation to each of my observations, then I get this equation, I get that equation, and I get that equation. I keep on going down. I look at that and go, hey, That feels kind of familiar. I've got all my y's on the left-hand side. Could I just make this into like a vector of y's? Yeah, I can. Let's do that. Now here, I see that I've got my betas multiplying by an x. Beta 1 times something with x1, beta 2 times something with x2, beta k times something with xk, right? All the way across. Could I represent the beta 1 through beta k and the x's in matrix multiplication? Yeah, I could. Now, what about this beta 0 stuff, my y-intercept? Well, that's just being multiplied by 1, right? So instead of having a random variable, could I put a 1 on the matrix? Yes, I can. So I can represent all of this junk over here with a matrix with a constant ones, my observed data, and then I multiply by a vector of betas. Okay, now over here, this is going to be my random term. They're hanging out over here. I'll go ahead and I see that I don't have any multiplication by an x value, right? So I'll go ahead and just do matrix, or I'll do vector addition onto this. And so this gives me the equation that y is equal to x times beta plus the epsilon vector. All right, so this is nice because now now that I've got the equation in terms of matrices, I can use all that junk that we did in chapter 2, all the linear algebra, the matrix algebra, all that goodness can now be invoked into this to make a lot of things quick, easy, and speedy, like easy peasy lemon squeezy. All right, so now let's scroll down. All right, so now I have assumptions, right? And when you make an assumption, you make an ass out of you and me. Aha. All right, well, in mathematics, we have to make an assumption or things are just not going to happen. We'll never get off the ground. All right, so let's rewrite those assumptions in terms of matrices. So the first assumption was just saying that the model is coherent. That makes sense, that it's a reasonable model. All right, well, I can say that in a matrix format is that the expected value of epsilon is equal to the 0 vector. That's a little bit more compact, right? Now here, I should be saying condition on x. I dropped that. Your textbook does not condition on x. I feel like he should be keeping that in there. That's kind of an implied aspect to the notation, and that's something that I feel like should be explicitly stated, but it's in there. Now, the expected value of y given x is x times beta. And now the next one, this actually has two assumptions packed together. So we had our second assumption and our third assumption. Our second one was saying that we had constant variance. Our third assumption was saying that we had independent observations. Well, if I have covariance of zero. So if I have covariance of 0 and I take a covariance matrix, I'm going to have zeros off of the diagonal, right? Okay, now if I have constant variance, then my diagonal of the covariance matrix is going to be a constant. Well, that's going to be a diagonal matrix with the same values along the diagonal. All right, well, what's that going to be? That's going to be that variance parameter, sigma squared, times the identity matrix. So here, the diagonal tells me that we have constant variance with respect to x. And then the zeros on the identity tell me that we have covariance equal to 0. So both assumptions, 2 and 3, are getting slapped into this one line put together. This is very powerful. Okay, so now we need to make some assumptions about the data. Why are we going to do this? So that the math works out nicely for us. Because this is not a numerical linear algebra class, we are not going to emphasize the pathogenic cases. If you were to go through and try to like rebuild SAS, if you were going to go through and rebuild R, SPSS or something like that, you'd have to worry about the pathogenic cases. We're not going to do that because we're lazy. Okay, so our assumptions about the data. First and foremost, I have more data points than I have predictor variables. And when I say predictor variables, that includes the constant for the y-intercept. And the next thing I'm going to assume is that we have full rank. So when I say full rank, that means that every column cannot be represented as a linear combination of other columns. All right, so this is important. If I have one column where I can go through and combine the other columns to get this one using, just by multiplying by a vector, then it's not a full rank matrix. We are going to assume that we have full rank. This, so in a way, this is like saying we have no redundant variables. So for example, let's say I have 3 variables. If I have 3 variables, say I take the first 2, I add them together, I get the second. I'm able to get, sorry, third. I add these 2, I get the third vector. All right, this one, the informative value here is actually contained in these 2, because if I add these together, I get this one, then this really is not adding anything to my model because of the mathematical structure of things. So I don't want this. I want to get rid of it. So I want to keep it simple. And full rank is just saying we don't have a redundant variable situation. All right, so something that we need to be mindful of whenever we build models. Let's say I build 2 models using R or SAS or something like that. And I build this model, beta 0, beta 1, x1, like this. And I go ahead and I fit the model. And then I fit another model where it's beta 0, beta 1, x1. Now, I throw on x2, beta 2 times x2 into the mix. Okay, so you can expect that the beta 0s in these 2 models will be different. The beta 1s in these 2 models will be different. If x1 and x2 are orthogonal to each other, then the adding the beta 1 and beta 2 are not going to change each other. All right, so let's take a look at an example. All right, so this is a ridiculously stupid example, but I hope this kind of gets the point across. All right, so let's say that my target variable is 1 through 30. This is my observed data. My first predictor variable is 1, 2, or 3 in order. So repeatedly, I've got a third of my data is a 1, a third of my data is a 2, a third of my data is a 3. And then x2, 1/5 of my data is a 1, 1/5 of my data is a 2, 1/5 of my data is a 3, 1/5 of my data is a 4, 1/5 of my data is a 5, and it's in order. So everything is in order. Now, why am I doing it this way? Just so that we can kind of see some stuff that comes out. So if I look down the list, the Y's are just 1 through 30. The X's are 1, 1, 1, 1, 1, then 2, 2, 2, 2, 2, 3, 3, 3, 3, 3. Then when I get to x2, I repeat 1, repeat 2, repeat 3, repeat 4, and repeat 5, like that. Okay, so we can see that as either x increases, the y value also increases. Okay, so let's build a model with just x1 as a predictor. All right, so I can see that I have negative 4.5 and 10 are my coefficients. So slope of 10, y-intercept of negative 4.5 is my fit. Okay. Let's build another one. Now, let's predict y using only the values 1 through 5. Okay, let's see what happens. Well, now I have a y-intercept of negative 2.5 and a slope of 6. All right, now what's going to happen when I put the 2 of them together? When I put the 2 of them together, I get numbers that are very different from what I've already seen. I get negative 3.6 about, 2.7, and 4.5. Okay, so both, like all 3 of the numbers changed when I put in another variable. Why is that? Well, because the x1 and the x2 have positive correlation with each other. All right, well, now something I can also do, and I'm going to come back to this a little bit, but this is the next part of the code shows us how to compute these values using matrix operations. But we're going to skip it. I hope this makes you excited for what comes up in a moment. All right, so now we want to talk about estimating the coefficients in our model. When I first wrote this out, I was going to estimate sigma squared, but I decided to cut the video short. All right, so we want to do the least squares estimate of our betas. Okay, so why are we doing least squares estimate? like if you look at ridge regression, you look at lasso regression, you look at Bayesian statistics, those are other ways to do, to fit a model like we've been talking about. And there are multiple ways to go about it. And there's other ways other than that to go about fitting a linear regression model. But what we want to focus on is on least squares estimate. Why is that? First and foremost, it has some nice properties in terms of statistics. So that's really nice. It's easier to compute some stuff. Like we're just using like really stuff that's just a little bit more advanced than Calc 1 to figure out what's the parameter estimates. It's a lot less complicated than things like lasso regression. So like if I wanted to, I can compute this. Also, the matrix algebra for doing this works out really nicely. So it ends up being really fast and it's stable. So, you know, there's a lot of advantages to the least squares estimate. There are a lot of disadvantages also. Usually when you start talking about ridge regression and lasso regression, the first thing that the professor talks about is all the disadvantages of least squares estimates. Definitely correct. Definitely a good way to go. But, you know, least squares estimate is still a good way to go. Even when I plan on using another model, I almost always do a least squares estimate first to guide me on what's going on. I find it's a good way just to give me information about collinearity between models. I find that it's a good way to kind of get a feel for how things should be looking as I work through. Using it for spotting like collinear predictors, I find it is very useful. So even if I'm not actually going to use a least squares estimate model for my machine learning, I usually end up building the model anyway, just to kind of give me a feel for what's going on as I wade through it. An advantage of standard linear regression is that it honestly tends to not overfit. And so whatever your test statistics are for making predictions, it's usually a good indicator of how your model will actually perform when you are making predictions on your score set. Like, you know, it's a relatively simple model, so it's hard to overfit on. You know, so if you do something like, you know, stochastic gradient boosting, you can overfit like really, really easy on that. Like, you know, if you're talking about like stochastic gradient boosting, you know, like every darn Kaggle competition has been won with that, but nobody talks about like how many people overfit with stochastic gradient boosting. I feel like that's like, it's sexy and people talk about it. Why do people talk about it? Because, you know, like when you hit the home run, you hit the home run with stochastic gradient boosting. The problem is when you don't hit the home run, you get beamed in the face with a ball. So for professional use, I don't use that strong of a fitting model. I would honestly rather use a low speed, simpler linear regression model where I have more faith in that it's close in what's going to happen. You always need to be worried about overfitting when you do real model building, because you would rather underfit than overfit when it comes time to explaining the output of your model and why things did or did not go the way you wanted it to. Okay, so for least squares estimates of our betas, remember, we absolutely must have our two assumptions. First and foremost, the expected value of the random term given x is equal to 0, and that our covariance of the random term given x is equal to sigma squared times the identity matrix. All right, so remember, this is telling me that the expected value has that relationship between the x's and the betas. So the model makes sense. That's what this assumption tells me. This one tells me two things: constant variance with respect to the x. Second one is that we have covariance 0 between observations. If I do not have those three things, I do not want to be using this type of model. All right, so here's my model. Well, actually, sorry, let me back up. So let's go ahead and let's say, you know what? I don't know what the true betas are. So what I'm going to do, I'm going to estimate them. I'm going to make a best guess on what beta 0 should be, beta 1 should be, beta 3, beta, and so on. And I'm going to go ahead and call my best estimates like beta hat. Right? I mean, that makes sense. So here's my estimate. For the moment, we're not going to worry about how we got that. And so here, I can build a model with that. So I'm going to take my best estimate of the coefficients, because I don't truly know what they are. Remember, when we're doing statistics, we never truly know what we're doing, because if we did, we wouldn't be using data. Okay, so my betas multiplied by my x's to give me my modeled value of y. The epsilon is going to be the difference between the true value and the modeled value. All right, so my goal is to find the best possible betas. Okay, so our game plan is to minimize the sum of squared deviation between the model and the observed values. Okay, so what I want to do, I'm going to take each of the epsilon values, I'm going to square them, and I'm going to add them up. So it's going to be epsilon transpose times epsilon, and that's epsilon half as the observed difference, the observed residuals. All right, so what we want to do, we want to find the beta hats so that when I put beta in for these coefficients, so here I've got the alpha as the coefficients, I want to find the minimum possible value. Why is that? Well, because if I'm minimizing the sum of squares, then as a whole, my model and my y are pretty close to each other. It's a good estimate. Now, we don't necessarily have to do sum of squares difference. We could also do like the sum of the absolute value, where that would be we could do like the mean average difference in, mean absolute value difference is, mean absolute error, that, the MAE, or MAD, depending on how you want to call it. I feel like those are actually better measurements for real life modeling, but absolute values are kind of hard to work with in a theoretical sense. Squares are very nice. We get everything from Hilbert spaces to work with very nicely. We get the topology works out easier to work with. Let's see what else. Oh, like we get calculus for free because it's just a polynomial. I mean, everything works out better. So all the theoretical aspects of sum of squares is much better. So if I'm working on a theoretical framework, I'm probably going to be doing sum of squares. If I'm doing a machine learning point of view and I want to do like real life, I find that the average absolute value deviation is a better measurement. The MAE is a better way to go than this. Now, something to always be mindful of is that our model value is estimating the expected value of y given x. It's not actually estimating y, because y is observed at that point. All right, so something that is important to always remember is that I need to have a full rank matrix. And when I say full rank, I'm saying that I have more observations than I have parameters to fit. So it's more coefficient. I have more observations than I have of coefficients. All right, as long as I have this going on, the minimum for the least sum of squares exists. So in mathematics, the existence of something is a big deal. Well, I'll go a little bit further. It exists and it's unique. If I do not have full rank, or I do not have enough observations, then the uniqueness of the minimum will not be unique, or may not be unique. All right, so here's the theorem. If y is equal to x times beta plus epsilon, x is an n by k plus 1 matrix. The rank of x is k plus 1. It's full rank. And we have more observations than I have coefficients to fit. Then beta hat that minimizes the sum of squares of residuals is equal to this matrix equation. So I have x transpose x inverse x transpose y. All right. As a professional statistician, you need to memorize this, and you need to remember, and you need to memorize this proof. This is an important one to have in your head. Okay, so I'm doing a minimization, and I've got something that is squared. Squares are kind of like polynomials, right? So we're going to be doing calculus on this. All right, so let's do our proof. All right, so I'm going to take observed residuals transpose times observed residuals. And that's going to be our sum of squared deviation. All right, so what I'm going to do, I'm going to just do my matrix multiplication. I'm going to rewrite this in terms of matrix and do the multiplication. And I get all this stuff. Okay, so now, what I'm going to do, I look at this and I go, hey, I'm trying to minimize with respect to the beta vector, right? Beta hat. I want to do calculus. All right, so remember, I do calculus. I set it equal to 0. That will either give me a maximum, a minimum, or an inflection point. Okay, so I take the derivative with respect to the beta hat vector. That gives me this. Okay, I'm doing calculus. So take the derivatives equal to 0 is how I find my maximum, minimum, and inflection points. All right, so I'm going to set this bad boy equal to 0. So I know that this y transpose x has to be equal to x transpose x beta hat. Boom, I've got this. Okay, so now we know this is to be true. Now, this equation is true regardless of whether we have full rank or not, by the way. But now we're going to use that full rank aspect. X is full rank and we have fewer columns than we have rows. That tells me that I can take the inverse of this x transpose x. Since I can take the inverse, I can multiply both sides with that inverse, and that's going to make the x's on the left cancel out. All right, so now that tells me that, so at this point in the proof, I know that when beta hat is equal to this, beta hat is either a maximum, a minimum, or an inflection point. Okay, so which one is it going to be? And frankly, it's multidimensional, so it could be multiple. Well, let's think about what's going on. If I think about the sum of squares aspect, if I was to expand this out, if I was to rewrite this whole thing, this whole ugly summation, I expand things out and I regroup things in terms of the beta 0, beta 1, beta 2, and so on, then what I would see is that this is actually a quadratic equation, or a bunch of quadratics on each of the betas added together. So if I turn my head on this, so now I'm looking at this in terms of the betas, not in terms of x and y. If I expand this out, and while I'm doing this calculus, while I'm treating the betas as being the variable, because at this point, I'm dealing with observed data. Since I'm dealing with observed data, the x's are observed. That means that they're constant and fixed. The y's are observed. They're constant and fixed. Okay, that means that in this stage of the game, the betas are the variable. Okay, if I was to rewrite this, rewrite all of the betas, span that whole thing out, get all that stuff out of there, I'm going to see that this is a sum of quadratics on each and every one of the betas. All right, well, think about that for a moment. What does the shape of a quadratic look like? It looks like a smiley face, right? Or a frowny face. Well, if I'm talking about maximums and minimums, like quadratics as I go far out to the left or far out to the right are going to go to plus or minus infinity, right? Okay, so, and these terms are always positive. These terms are, or zero, they could be zero. These are positive or zero. Okay. Well, if I think about that, since I'm adding up a bunch of things that are positive or zero, it always has to be a non-negative number. And I can have those betas keep on going far out to the left or right. So I can increase each of those individual quadratics. So that tells me that I could keep on getting the magnitude of this thing bigger and bigger and bigger, however big I want. All right, what that means is that this derivative cannot give me a maximum because I could keep on getting it bigger and bigger and bigger. If I can make it bigger and bigger and bigger, I don't have a maximum. So I know that that's not an issue. So that tells me the beta hat is either a minimum or an inflection point. Okay, so what I'm going to do, I'm going to do a proof by contradiction. Let's say that beta hat is not a minimum. Okay, if it's not a minimum, then I can find something that's better for minimization, right? All right, what I'm going to do, I'm going to say lowercase b, is that better minimization? Okay, well, just from that statement right there. So prove by contradiction, I make the assumption that such a B exists. Since such a B exists, I know that this inequality is true. Okay, well, let's go ahead and see what happens. If I take this left-hand side, what I can do, in the middle, I'm going to add and subtract x beta, x beta. Okay, I should have hats on here, all right? If I had a whiteboard. If I had a whiteboard. So I'm add and subtract x beta hat, add and subtract x beta hat. Now, if I add and subtract the same term in there, does it change anything? No, it doesn't. It just makes it more complicated, which is what we like to do in math. Okay, so once I get to here, and please put a hat on these betas, I can go ahead and expand that out with the matrix multiplication. All right, so I go through and I expand it out, and I'm going to get these three terms. All right, so I get here with beta hat involved. Here, I've got the difference between beta hat and the minimization of B. And then I have x transpose x. And then I get this part. Okay, now, let's think about things for a moment. Remember, I did a derivative. I set the derivative equal to 0. Do you remember how that looked? I'm going to scroll up. All right, remember that when I took the derivative and set it equal to 0, that means this whole thing is equal to 0. Well, if this is equal to 0, then x transpose x beta hat, x transpose is equal to x transpose y. These two are equal to each other. So if I subtract one from the other, I get a big fat 0. Okay, so if I look here, that's exactly what I got here. I get subtraction. So I know this has to be 0. Okay, so I know that this term is out. Okay, well, let's keep going. Well, what do I have here? I have x transpose x. And x transpose is a full rank matrix with more rows than columns. All right, what that tells me is that this bad boy in the middle is positive definite. It's positive definite means that the only way I can get something like that, so I can't get anything negative, and the only way I can get 0 by multiplying with the quadratic form is if the vector is equal to 0. Okay, so if this is equal to all of this junk here, just this one line, all right, oh, actually I have it written down here. So my true minimum is equal to basically the same thing, but I'm using beta hat in here, and then a positive definite term. Well, I know that this has to be less than that, right? But how can I have that if it's positive definite? I mean, this has to be greater than 0 because it's positive definite. The only way it can be 0 is if beta hat is equal to B, which tells me that I have a contradiction. Since I have a contradiction, beta hat has to be a minimum. Now, something that's nice about this, since we're working in finite dimensions, and if you take a topology class and work out some of these details, you'll know that from the work that we just did, it comes out for free that the beta hat is unique. The minimization is a unique value when we have full rank matrices and we have more data than we have coefficients. All right, so now what is x transpose x? Here's a way to write it out. But if I want to put it in matrix form, I can put it this way. I have n, and then I have the sum of x's. This position that I have along the diagonal, I have sum of squared x's, and I have terms of the product between the x's on the off diagonal. Here's x transpose times y. Here is our epsilon vector. It's just the difference between the model and the observation. And if I want to go through and I want to do simple linear regression, everything works out so nicely. All right, now I want to go back to the computation I started earlier. So here, I want you to pay attention to these coefficients. Now, my data matrix that I just created, when I tack on a constant column of ones, and then I have the x of 1 and the x of 2 vector, and I call that x, so that's what I've got here. If I go through and I use these formulas, I'll end up getting negative 3.59. If I scroll up, negative 3.59. Coefficient for x1 is 2.7. I scroll up, we have 2.7. And then coefficient of x of 2 is 4.5. I get 4.5. So we can, if we want to, we could actually manually compute the coefficients using those formulas. It's actually better to let the machine do it. Use the functions that are built into R, or SAS, or SPSS, or Python, whatever you want to use, because those functions are built in, able to handle cases where you don't have full rank, when you don't have linear independence between your predictor variables. When you use the matrix formulas as we present them here, you're basically making you're making not huge assumptions about your data, but if you're in a small data situation, you can have problems. Usually the one that will come up is you can have collinearity problems. But that's all I've got for you. Take care and goodbye.